Welcome everybody to Stat 243. I believe this is lecture number 6. And we're going to start chapter 4 in both the Baymard and the OpenStax textbook, which is all about discrete and binomial probability distributions. So we skipped chapter 3, which is fine. So far, we've been working with data. Which are sets of observations or samples taken from a population made up of individuals. And that's the ultimate goal for statistics, right? To understand systems and populations. Probability distributions, which are different, are like a tool that helps us model populations. So data from a set of observations taken from a population is one idea that we study in statistics. The other is a probability distribution, which is a set of possible outcomes along with associated probabilities for each outcome. And the first thing we're going to do actually is we're going to get a set of cards and we're going to generate some data from this probability distribution. So you can follow along if you want. As soon as I draw the first one, I'm going to pause the video because I'm going to be walking around the classroom. But let's collect data from a probability distribution. There's an abbreviation generated by drawing a card at random. So I'll take the cards and I'll shuffle them. And I'll draw a card at random. We got a 9. So starting our data. Now I'm going to pause the video. And by the time I start the video, we'll have a full set of data. All right, there's our data presented as raw data. What's the most common observation? 9, I think so, yeah. So this is data drawn from a probability distribution. The best way to collect data from a probability distribution is repeated random sampling. In this data collection methodology, whenever someone picked a card and flipped it over, I put it back in so that it could be drawn again, which is how you really need to do it with the probability distribution, because it should be an equal, you should have a chance of pulling that number every single time. So that's called sampling with replacement. Sampling with replacement means the same outcome can occur again with its associated probability, even if you already picked it. And the other one is sampling without replacement. This means once an outcome is picked, it can't be chosen. It cannot be chosen again. This changes the probability distribution every time you sample. So it's not a great way to understand a probability distribution. All right. So let's talk about another way to look at this data. Instead of looking at the raw data, we could do what with it to understand it a little more quickly, maybe. Let's make a frequency table. Yeah. They're cards, so they're face values, but they don't really have, other than the fact that it's, you decide what a card is based on the number, it doesn't really have a numerical value to it. So at most, I would call this probably categorical ordinal data. You could say that a 9 card has a higher value than a 3 card, but it's all just ways to label the cards. So since this is categorical ordinal data, a frequency table would be a good way to look at this data to try to understand it a little more quickly. Let me do this for the moment. And once we get into the frequency table, it's all right if we don't see the raw data anymore. Oops. Another good place to start is with our most foundational summary statistic, which is how many observations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I counted 21 observations. There were only 10 cards. So definitely some of these cards got picked more than once, but that's okay in a probability distribution because we're sampling without replacement. Sorry, with replacement. The number of observations is not necessarily the same as the number of outcomes. In fact, it's usually much bigger. Than the number of possible outcomes for discrete data. And the reason for that is it's a pretty big distribution if there are more than 30 possible outcomes. But having a sample of size 30 is a good idea. So, all right, 21 observations. Let's do the face value here. And the number of observations here. So the smallest face value was 2, right? And I see that the number 2 was drawn twice. Next smallest face value was 3. And it was drawn 5 times. Next smallest face value was 5. And you can't see the raw data anymore, but that's okay, I can. That was drawn twice. And then there was an 8 that was drawn also twice. And then the 9 I count 10. Add those all up. Total observations, 21. Good. Let's go a little farther and let's do a relative frequency table. Let's add that on. So this would be the proportion of observations. So we got 2 out of 21 is a 0.095. 5 out of 21, 0.24 approximately, 0.24, and another 0.095, 0.095, and 10 out of 21 is going to be just less than 50%, 0.48. What should it add up to? 1, which is the same as 100%. Yeah. And we're going to be close, but since I did some rounding, we probably won't be exact, but that's okay. All right. So how do you understand a probability distribution? There are 3 ways in order of increasing effectiveness. One way is to take a sample, which is what we just did, ideally a sample with replacement, and calculate proportions. That's what our relative frequency table gave us. Based on our relative frequency table, what do you think is the probability of selecting a 3? %, 0.24 or 24%. I'm happy with either way of thinking about it. On occasion, your homework will be picky and want one or the other. And Hadley, why did you say 24%? Yeah, exactly. With a single sample, the proportion is the best guess for the probability. With a single sample, your best guess for probabilities are the proportions. But those are probably not going to be very great guesses, especially if we only have 21 observations. Now, if we kept picking cards for the full class period and ended up with 300 observations, then our proportions might be fairly accurate. But with just 21 observations, we're not going to be as accurate because that's really not enough data to fully understand at least a discrete probability distribution. If you have more time and resources, your next option is to repeat the sampling process and then average the proportions for all the different samples. These average proportions are called experimental probabilities. This is about as good as actual statistics can ever get. at least in the real world. Because there's always chance, right? So even if I repeated, even if I collected this data, I use the same set of 10 cards for every class. This is the third time I've done it. Even if I kept doing it for my whole career and ended up with 100 different classes where we did these samples, those experimental probabilities might not still be totally accurate, because in statistics, we never expect to be totally right. So instead of just having this one table, we might have 10 different tables like this. And then we average these proportions for every table. And we think that's going to get us a better idea of the true probabilities. The third way is to explore the mathematics to develop theoretical probabilities. Almost every probability distribution can be modeled with mathematics. And as soon as you put it into math, you have tools to explore the probabilities. This last one is the one we use most often in classical statistics, because we use a mathematical model to represent a population. So often, we use a probability distribution to model populations. And then we use theoretical probabilities to understand the population. And we will be doing that basically from here on out in the class. So one big reason to study probability distributions is we use those as one of our tools. Remember that statistics is a mathematical science. That's one of the three types of science that I call it, because we use tools from mathematics to help us. And this is one of those key tools. When you flip a coin, what's the probability that it lands on heads? 50%. But how do you know that? Have you flipped every coin in the world as many times as is possible? No, it's because we understand if it's a fair coin and there are only two options, it's got to be 50-50. That's a mathematical understanding and a theoretical probability. If we actually sat here flipping coins, we might not get exactly 50 out of 50, but we know that's what it should be. Yeah.
It's actually about 52 because heads is slightly heavier.
And that's a better mathematical model of flipping a coin, right? It doesn't mean that you can't model it mathematically, but maybe you can improve your model just a little bit. That it's actually 52%. I don't know if I would go that high, but maybe a little bit off of 50 because of the different weights of either side. And of course, a penny would be different than a quarter. So now we can explore the mathematics of these cards. And in this case, we're just going to explore them by looking at what the card values are. So I have 1, 3. I'll start with 2. I have 2 2s, 1 3, 2 5s, 1 8, and 4 9s. All right, so we can make a probability distribution which looks an awful lot like a relative frequency table, but it's the exact values. So let's do it. Let's write down the theoretical probability distribution. And in the future, I won't use the word theoretical, but the theoretical probability distribution based on our mathematical exploration. In this case, the math was we just looked at the cards. So we have the value here and the probability here. Remember, there were 10 cards. So a face value of 2, there were 2 out of 10 of them, or 0.2. A face value of 3, there was only 1 out of 10, or 0.1. Face value of 5, there were 2 of those, 0.2. Face value of 8, there was 1 of those. And a face value of 9, there were 4, 0.4. This is a probability distribution. This is a discrete probability distribution. The definition of a probability distribution: a set of possible outcomes along with associated probabilities for each outcome. There we are. The face values are the set of possible outcomes. Associated probabilities are right here. So based on the theoretical probability distribution, what's the probability that someone would select a 3? 10%, 0.1, 1 out of 10. Notice that's different than our proportions because we don't ever expect to be exactly right. Our proportions, just to remind you, was 0.95, 0.24, 0.95, 0.095, and 0.48. They weren't terribly wrong. We did get 9 most often. It's interesting that 3 was one of the least likely, but we got it a lot more than we got the 8. Each time I do it, we get a different one. One of my classes last term, nobody picked an 8. So as far as we know, 8 wasn't even in the deck, right, until we investigate it mathematically. That's called a black swan event. When people from England, the British, when they first went to Australia, they'd never seen black swans before, which are native to Australia. So if you had asked a Brit in, I don't know what, 1803, what's the probability that there's a swan that could be black? They'd say 0, because they'd never even imagined it. And black swan events are really challenging for statistics, because how do you put the probability on something that you don't even know exists? Okay, so this is very important because this is how we show a discrete probability distribution. The easiest way to show a discrete probability distribution is in a table. When we get to continuous probability distributions, the easiest way for that is to show it in a graph. And then there's something in the middle, which is a binomial, where we could use either. But let's explore this a little bit more. Focus. Okay. I'm going to rewrite it up here just so that we have it for reference, just nice and small. 2, 3, 4, not 4, 2, 3, 5, 8, and 9. This is the value, and this is the probability, 0.2. If you just want to write it one time in your notes, that's fine. I just want it up here so that you all can see it when I refer to it. Okay. Focus. Focus. Okay. So suppose the face value represents an actual quantity. So we're walking away from saying it's categorical. We're now saying it's quantity. Maybe it's the number of dollars. Maybe it's the number of cats. Maybe it's the number of hats. I don't know. If you picked an outcome at random, what is your best guess as to the quantity that you get? Pause the video. I want you to talk about this with your neighbor. There's a couple of reasonable answers. There's one that we're going to pursue more in depth. But I'll pause the video. Talk about it with your neighbor. Decide what's your best guess as to the quantity that you would get. So if I just picked one card, I guess for me, I would probably say I'd be most likely to get a 9, just because it's the most common observation. But picking one card is not great statistics. What would be a better question would be, what if I collected a random sample that is reasonably large? What's a good size for something that's reasonably large in statistics? Yeah, 30 or more, right? And at least 30. And averaged the values on the cards that I picked each time. What is my best guess for that average? That's a more interesting statistical question because it implies that we're doing good statistics by getting enough data. And there's a nice mathematical way to figure that out. To figure this out, what we do is we take each outcome multiplied by its probability all added together. So we would take on the first outcome, which was 2 times its probability, which is 0.2. And then we would take 3 times its probability, which is 0.1. And we would take 5 times 0.2 and 8 times 0.1 and 9 times 0.4. And we'd add all of those up. At the end, we get hold on, I'm doing it here. Let's see, 2 times 2 plus 3. 6.1. The name we give to this number when we're talking about probability distributions, we call it the expected value of the probability distribution. If any single observation is X, then the expected value we write as E parentheses X, expected value of X. Mathematically, the expected value is also the mean of the probability distribution. Using our Greek letter mu, so you might see mu. And in fact, this process for calculating it is completely analogous to how you calculate the mean of a sample of data. It's basically adding up all the observations and dividing by the total. Okay. So our best guess, if we were to draw, let's say 30 cards and average the value on the faces, would be 6.1. Do you think we'd get exactly 6.1? I see heads shaking. Why do you think we wouldn't get exactly 6.1? Well, first of all, there's no 6.1. You definitely would not draw 6.1 as a card. Yeah. But even if I draw 30 cards and average them, an average could be 6.1, right? An average could be a decimal. But do we think we'd always get exactly 6.1 when we do the average? Gabby, you want to venture a reason why not? Because of the randomness, yeah. Right, the randomness is the reason why we never expect to be exactly right in statistics. It's not because we do it bad or because the math is bad, it's because it's the randomness. So the expected value doesn't mean the average you're always going to get. The expected value is the number that you expect to be close to and what could you do to get even closer? If I wanted to get even closer to the expected value with my sample average, what could I do? Get a larger sample, collect more data. Yep. The expected value is the number that you expect to be close to when you average, and you expect to be even closer if you increase the sample size. Let's test that. I've got the data here. 9 plus 9 plus 9 plus 3 plus 9. All right. So the data we collected, our sample average, our sample mean was 6.43, which is pretty close to 6.1. That's good. It means our sampling methodology was probably pretty reasonable. But it wasn't exactly 6.1, of course, because that would be super surprising, right? To get exactly the average, I would be surprised. Now, if we had not stopped at 21 cards, but if we had done 100 cards, we would probably be even closer to 6.1. This is another reason why simply drawing a single card is not a good idea. You're not going to be very close if your sample size is 1. If you want to understand the distribution, you got to draw enough cards so that when you calculate statistics, they are reasonably close to the actual properties of the probability distribution. Okay. So this process is important. This process of taking the outcome value times its probability and adding all of those up. In fact, not on the, on the first quiz, I think I asked you to do that. So you should be able to know how to do that because chapter 4 is going to be on the first quiz. Um, discrete probability distributions. They also have standard deviations. Calculating them is possible through a hand calculation, but we're not going to do these calculations. In this class. Maybe if you take another statistics class, you will. And what the standard deviation tells you is, just like with data, about how much you expect your individual observations to vary away from the expected value. I should have pre-computed the standard deviation for this, but I didn't. I think I did it before. It was something like 2. The standard deviation was approximately 2. So if we take our expected value, which was 6.1, and our standard deviation, which was about 2, and we think about this on a number line, here's 6.1 in the middle, a step size of 2 to either side takes us between about 2 and about 10. And that pretty much covers the entire possibility for this probability distribution. So again, it's a good single number that describes how spread out that probability distribution usually is. Now let's talk about the most common and most, probably the most important type of discrete probability distributions, which is called a binomial distribution. Binomial, just like binary, means there are only 2 possibilities. And in fact, if you were to call this a binary distribution, I'm okay with that. It's not really the word for it, but it indicates that you understand that there are only 2 possibilities. It could be 0 and 1, it could be heads or tails, it could be true or false, it could be yes or no. But the key is there's a probability associated with that instead of just data. So our most common is flipping a coin. Assume 50% probability for heads or tails. Even if it's not exactly 50, let's go ahead and assume that. It's a good mathematical model. So we can do a theoretical probability distribution for a single coin flip. What are the possible outcomes? Yep, it could be a heads or it could be a tails. What's the probability on each? 50% or 0.5. That is an extremely boring probability distribution. What's nice is it's pretty quick to understand because there's not a lot there. What we do instead is we think about not flipping 1 coin, but let's flip 10 coins or 30 coins or 600 coins. And let's count how many heads there are. So a binomial distribution flips a large number of coins, call it n coins, and counts how many are heads. Call this number X, or some books call it K. I think your book calls it K, but our online app calls it X. So let's just do this, and let's explore a little bit. Let's suppose I'm going to flip 4 coins. The first coin could be heads or tails. Suppose it's heads. The second coin could be heads or tails. Suppose that's also heads. And so is the third, and so is the fourth. That's a possible outcome. Of course, I could also have the first 3 be heads and then the last one be tails. Or maybe the first 2 are heads and then there's a tails and then there's another head. Or maybe I have a head, a tail, a head, a head. Or maybe a tail, a head, a head, a head. Each of these are outcomes. But getting 4 heads, we call an event. So the outcome is heads, 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 tails, but we group all of these together and we say 3 heads, that's the event that I'm actually interested in. Outcomes can also be events. Like if we just flip 1 coin, a heads is an outcome and it's also an event. An event is a group of outcomes. Okay, well, I could have had 2 heads and 2 tails. There's a couple of different ways that could have happened. I'm collapsing. There we go. That's the event where I get 2 heads. Or I could have just gotten 1 head so that 3 of them would have been tails. Heads, tails, tails, tails. Or I could have gotten no heads. And that's my full probability space. Those are all the different, I can almost fit it, but I can't. Those are all the different possible outcomes grouped into 4 different events. 4 heads, 3 heads, 2 heads, 1 heads, or 0 heads. So rather than trying to build my probability distribution on these outcomes, let's build it on the events instead. So here's my binomial probability distribution from flipping 4 coins. I could have had, this is the outcome here. And then the, oh, sorry, I don't want outcome. I want event. So I'm going to start on another page because I ran out of space. Binomial probability distribution or binomial distribution for 4 coin flips. So my event and the probability. I could have 4 heads. So we go back and we say, out of all the possible flips, how many were 4 heads? 1, how many possible outcomes were there total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 16, which by the way is 2 to the 4th. So there was 1 way to get 4 heads. There were 16 total. Check your notes. How many ways were there to get 3 heads? Show me with your fingers or just tell me. There were 4. And 16 total possible outcomes. So that's 1/4. I'll go ahead and put the decimals as well, if I can do that math in my head, 0.0625. Or I could have gotten 2 heads. That was the event I probably see most often. And that had 6 ways. So 3/8, which is 0.3125. Or 1 head, which is the same as 3 tails. So that's 4 out of 16. 1/4, 0.25. Or 0 heads. That only happens if they're all tails. There was only 1 way to get all tails. 0.0625. And if you add all that up, it should add to 1, because if you flip 4 coins, you're going to get something. Yeah. Now, keep in mind, 4 heads is the outcome. It's not that there are 4 of the heads and 16 total, right? There's 1 way to get 4 heads and 16 possible sets of outcomes. What's the expected value of this distribution? There's a couple different ways to do this. You could do it by taking 4 times 0.0625 plus 3 times 0.025 plus 2 times 0.3125 plus 1 times 0.25 plus 0 times 0.0625. That could work. But the expected value is also the mean, which is a pretty good measure of the center. Is there a center to this distribution? 2. It's nice and symmetric. 4 and 0 have the same probability. 1 and 3 have the same probability. 2 is right in the middle. Now pause for a moment and say, if I told you I flipped 4 coins, what's your best guess for how many of them would be heads? 2. That's exactly what the expected value is when it's a nice symmetric distribution, because 2 out of 4 makes the most sense. 3 out of 4 could happen. 1 out of 4 could happen. I might be surprised if all of them were heads or if none of them were heads. And another way to see this distribution is to make a bar plot. So binomial distributions are one of the discrete distributions where graphs are really useful. And you're going to do this in lab 2. Let's put our possible number of heads here on the horizontal axis. And let's treat the height of each bar as a 1/4 possibility. No, how about 2 bars is a 1/4 possibility. So 1 would be here. Zero is going to be down here, 0 heads. 2 is going to be brain, I think here. 3 is going to be here, and 4 is going to be there. That's a nice symmetric distribution. If I didn't tell you what this represented, but I said this is just some numerical distribution, what's the mean of this distribution? What would you say? 2, because it's right in the middle and it's symmetric. Binomial distributions, they're not always perfectly symmetric, but they definitely approach perfect symmetry. All right. Let's do a little more. How about instead of flipping 4 coins, let's flip 20 coins. Let we'll let X be the number of heads. What's the expected value of X? How many heads do you think you would get if you flipped 20 coins? I heard someone say 10. I agree, because it's either going to be heads or tails with an equal probability. Makes sense, 10. Should we make a table and fill out all the possibilities? Who wants to do how many heads there are? That's easy. There's one way to get 20 heads. How many ways are there to get one head? No, because it could come at the beginning or it could come in the middle, the next one, and the next. There's actually 20 ways. How many ways are there to get two heads? I don't want to do that math. So actually, it's fun math. I can show you how, but that would be in a different class. So instead, what we can use in our week 4 materials, yeah, I'm moving ahead a little bit because I'll stop after this. But what we can use is we can use this app for visualizing. That is new. They just blocked it. The other one works better. Okay, here's a secondary alternate, and I'll put this link in Canvas. But here we go. Flipping a coin has a 50% probability, and I'm going to flip 20 coins. There it is. Nice and symmetric. 10's right in the middle. And if you hover over it, it tells you that the probability of getting exactly 10 is 17%. Just because 10 is in the middle doesn't mean it's 50% likely, right? Because it's certainly possible to get 9 out of 20 heads or 11 out of 20 heads. It just means it's the most likely. And you can hover over and you can find those different probabilities. And even we can do something where it's not a fair coin. Like suppose it's 52%. That changes the probability of getting 10. Or maybe it's way off. Maybe we're not talking about flipping coins. Maybe we say 70% of Chemeketa students have taken Math 111. If I collect 20 random students, what's the probability that 12 of them have taken Math 111? And it shows us right there. All right, I got thrown off a little bit by the app that didn't work, but that's okay. What we're going to do on Tuesday is we're going to come back to this binomial distribution and explore it a little bit more deeply. But this will get you a start on both your homeworks and your next lab.